All right, folks, welcome back. Monday, the 11th of January for us now. What we're going to do today is we're going to start talking about kinetic energy and how kinetic energy plays a role in this. And don't forget, because work needs energy in order for it to move or to be able to do any work at all. Again, kinetic energy is just moving energy, okay, for us. So here we go. So like I said, kinetic energy is the energy of movement. Up on the top of the screen here, what you have is you have the formula. So Ke equals 1 half mv squared. You're going to want to add that to your formula list again. Now, I understand that formula list is getting a little bit large here. So that's why I'll keep showing you the kind of revised version of it and keep asking you to edit it and do stuff like that with it. Okay. So when we look at this, we ask the question, with the equation above, which variable causes a bigger change, the m or the v squared? Well, obviously it has to be the v squared, right? Because the change there would actually be squared instead of just, right? So in a hockey movie, a player hits a slap shot that knocks over a suitcase. It is rumored that he would have to create 480 joules to get a 0.105 kilogram puck. To do that, how fast would that be moving? Again, you may or may not have seen this movie. Yeah, anyway. All right, so we're going to use 1 half mv squared. All right. Now, the nice thing about this equation for us here is that when we look up here, we have energy and we have a mass, right? And we want to know how fast. Okay? When we plug our information in, we see we get 480 joules of energy, right? So that's our Ke. And then the mass just goes in the mass spot there, right? So get from the previous point to that point, I multiplied a half by 0.105. So I took 480 divided by 0.0525. Now I've got that equal to v squared, right? To isolate v all by itself, I got to take the square root of that. So after plugging it in my calculator, I find 9,143 equals v squared. So I end up finding that v is equal to 95.6 meters per second. Now, to be completely and totally transparent with this, that's probably a little unrealistic. That's somewhere in the neighborhood of about 190, 200 miles an hour, which I don't believe a person could get a puck to go that fast. Now, if it does exist, awesome. That person might get charged with murder for all of a sudden killing people or breaking glass or whatever. Anyway, so kind of how we're able to just use the equation just to find the energy of itself, right? Okay, now how to actually use this in kind of some more practical sense. So we're going to use what's called the work-kinetic energy theorem. Now, the work-kinetic energy theorem, I know that once you see the word theorem, all of a sudden you start to flash back to geometry. I did the exact same thing, right? Meaning that I started to look back when I first started to teach this a couple years back, I saw a theorem and I'm like, oh my gosh, I had flashbacks to Mr. Peterson's class. Now, you don't know who Mr. Peterson is, but he was my geometry teacher back when I was sitting in your seats. And yeah, it was, no, thanks. But no, it's not that. Okay. So we basically say the net work done on an object is equal to the object's change in kinetic energy. Now, like I started out at the onset of this lecture, what you're going to see is that in order to do work, we need energy. Well, just because that energy is moving doesn't mean we still can't do work, right? When we talk about work as force times distance, it's still a force over a distance. Now we're just causing a mass to go from one velocity to another velocity. That's all our kinetic energy theorem is all about. Okay. So again, make sure you write this one down. Work net equals our change in kinetic energy. Now, when we talk about net work, right, really this could be a couple different things. This could be, the work of the force versus the work of the friction against that object, right? And our change in kinetic energy could be maybe getting it from the start or getting it from a pre-existing velocity to a different velocity, all right? So yeah, we're going to see a little bit of acceleration here, or deceleration, if you want to look at it that way, but we're not going to use our fun equals my yet, okay? In other words, for us, what we see is you need to push on a thing for a distance to change how fast it's moving, which makes sense, right? Meaning that if we want to speed our bike up to get across that intersection, not that we're going to be riding a bike anytime soon here, but we need to push on it. We need to apply force. We need to increase that speed. All of those things give us that work kinetic energy theorem, right? So all of those things become important for us because that's a change in kinetic energy. All right. So one way to look at it is our net work equals 1/2 m and then VF squared minus VI squared. All right. If we distribute the 1/2 m, we get this or that. Now, all three of these are really great equations, to be honest. I like the top one, I like the bottom. Those are the ones that I really, really do like better, just because we can maybe find an initial kinetic energy, we can find final kinetic energy. Or we know an initial velocity, we know a final velocity, and now we can calculate that using the top piece of it. All right. So with that being said, let's try something out here. Okay. A certain teacher is driving his 2,650 kilogram Honda Pilot. All of a sudden, he pulls out in front of you on dot. How much work will the pilot have to do to go from 4.47 meters per second, which is about 10 miles per hour, to the necessary 26.8 meters per second, which is about 55 miles an hour, 60 miles an hour? Yeah. So what we see here is we've got a mass, right? And I've got a velocity and another velocity. Right? So if I see this, we're going to go from this velocity here to this one here, right? So that should tell me something. That should tell me this is my initial, this is my final, okay? So what we do is we're going to say, all right, work is equal to our negative, or is equal to our kinetic, or change kinetic energy, sorry. And that equals the final kinetic minus the initial. So if I branch that out a little bit and make my life a little easier, that's 1/2 m times VF squared minus VI squared. Well, the nice thing is that already we established that we have those variables. So it's going to be 1/2 2,650, which is our mass, and then we just take our 26.8 squared and subtract off our 4.47 squared, right? So if you take half of 2650, that's 1,325. Take 26 squared minus 4.47 squared, that's 698.3, right? Multiply those two together. We see that our work here is 925,195 joules. Yeah. So, sorry, I just had to see if I was going to change that into horsepower or not. Not that you have to do that or anything like that. Yeah. So that tells us, how much energy in the form of kinetic energy was required to get this thing up to that speed or to create that amount of work. All right. We could then translate that into a force and a distance if we wanted to. We could talk about how much friction that pilot encounters going on that Dodge street. Okay. All of that sort of stuff. All right. So new formulas are over here on the right. So do make sure that however you are doing this, you've got those new formulas ready to roll and ready to go. Okay? All right, last one. This one's a little bit more involved. This one has a few different prompts involved with it and will require a little bit more of your attention to be able to understand how to do this. Okay? So we got a 100 kilogram desk that's dragged across the floor with an initial speed of 1 meter per second. The pulling force is 1,000 newtons and it is horizontal. That's a big deal. All right, no angle or anything like that matters. The coefficient of kinetic friction is 0.4 and the desk is dragged 10 meters. How much work is done by gravity? Now, remember, the direction that gravity works is downward. So for us to talk about work done by gravity, we need this thing to actually be moving up and down, right? Well, in this case, none is done by gravity. The reason? Gravity only works if there is vertical motion. Because we're dragging this thing horizontally, right? Because we're dragging it side to side, that means all gravity's doing is holding it onto the ground, onto the surface that we're talking about. But there again, we're getting that normal force pushing back up against it as well. All right. So here's where we go. We ask how much mechanical energy is lost to friction? Work done by friction. 2, how much work is done by the 1,000 Newton force? 3, what is the change of kinetic energy of the desk? 4, what is the final velocity of the desk after being pulled 10 meters? All right. Pause it, give it a shot, see if you can do it. All right. So hopefully you tried it. If you didn't, that's fine too. Here we go. All right. So when we look at all this information, what we see is we've got the mass of a desk, right, dragged with an initial speed of 1 meter per second. The pulling force is 1,000 newtons, right? And the coefficient of kinetic friction is 0.4. The desk is dragged this. So we've got a distance here. We've got a mu there. We got a VI there. We've got a force there. And we've got a mass there. Holy cow, folks. We got a ton of stuff going on here, right? It's a little bit overwhelming, so let's just take this piece by piece, all right? So how much mechanical energy is lost to friction? So this is work done by the friction, right? So remember, what we need for friction is, if we're going to find how much mechanical energy is lost, how much work is done by that, we need our work formula, force times distance. Or we could do work equals GPE, but we don't have a vertical, right? So that doesn't work, all right? Friction is not actually speeding up, right? So it can't be work equals delta KE. So this one, for us, we have to think about what friction does. It turns mechanical energy into heat. Mechanical energy lost to friction, what that means is the energy is destroyed is just turned into heat, all right? So when we look at this, if we're losing it, that means it's trying to slow it down. So we're going to go, our work of friction is just our force times the distance, right? Because we're pulling this thing, friction is going to act backwards against it. So if we're pulling it from the left side of the screen to the right side of the screen, the work of friction is just acting from the right to the left. So what we have to find out is, okay, how far did this act? Well, that's a 10, right? Our force of friction. How are we going to find our force of friction? Well, remember now, we need to know, okay, is this 1,000 newtons a force of friction? No, that's our pulling force, right? That's the force that's actually applied moving that way. So then, how do we find our force of friction? Well, if we go back to our equation, this is going to be mu mg, right? So mu times our normal force, well, that's just mg right there, right? So we could actually replace that with just mg, right? We got our g up here at 9.8. Do we know the mass of the desk as we're moving it? Yeah, it's 100 kilograms right there, right? So what we're able to say is, all right, 100 times 9.8, so 100 times 9.8, that's where that 980 came from, right? Times our kinetic friction, or our coefficient of kinetic friction, which is right there, right? And what we see is we end up with a negative 3,920 joules. Wait, why is it negative again? Going the wrong way, right? It's opposing motion. So in this case, friction is not winning. It's actually losing. Because it's losing, friction has to be negative. Will it always be negative? Absolutely, right? All right, so we found our work due to friction. All right, so how much work is done by the 1,000 Newton force? Well, because we're asking for how much work is done by that pulling force, it's the same formula set up for us. We're just going to use force times distance. The difference in this case is it's actually winning because it's going in the right direction. So what we start to see is that applied force is acting over the 10 meters, right? Just like that friction acted over the 10 meters, all right? So we see our workforce here, and maybe this F isn't probably not the best thing to have there. Our work here is 10,000 joules. Maybe work of pulling is probably a better way to describe this one, okay? So third, what is the change in kinetic energy of the desk? Now remember, change in kinetic energy, we got two possibilities. It's either kinetic energy final minus kinetic energy initial, or it's our net work. In this case, we'll use our net work, all right? So with our net work here, the two forces that are acting is the work of the pulling force and the work of the friction, right? Because those are acting in opposite directions, that's why we made that work of friction negative, right? So when we add those two together, because they're both doing work on the object, it's just one's going to be negative because it's not winning. The other is going to be positive because it is winning, all right, and getting its direction. So what we end up seeing is this net work is 6,080 joules. That's how much work we're doing to pull this thing and speed it up, right? That also means that's how much we're getting in our change in kinetic energy. Now, side note, how much GPE are we getting here? 0, because we're not lifting this, right? Okay. Power? Well, we would need how much time it took. We're not asking that question yet. All right. Anyway, so now that we know our change in kinetic energy, part 4 says, what is the final velocity of the disk after being pulled 10 meters? Well, if we know how much kinetic energy, our change in kinetic energy is, do we know the mass of the disk? Yeah, it's still right up here. It's still at 100, right? We had to find our final. It didn't start at 0. It actually started at an initial speed of 1. All right. So we start plugging info in. All right. We got 6,080 equals 1/2 m. So 1/2 times the 100. That is multiplied then by VF squared minus our 1. Okay. So what we have to do is a couple options. You could distribute that 1/2 of 100 or 50. I don't want to do that. I'm just going to run it and basically divide it over. Okay? So I divided the 50 over. That left me with VF squared minus 1. And then added that to the other side. Okay? So to go from here, I divided by this. That left this bit all by itself, right? So I divided by my 50, right? That left me with VF squared minus 100. I then added the 1.0 over, right? So that gave me VF squared equals 121.6, right? So I square rooted that, and I found that at the end of all of this, the square root of 121.6 is my final velocity of 11.1 meters per second. This thing sped up about 10.1 meters per second over that 10 meters. All right. If we wanted to, we could find the acceleration. Okay. So when we look at this thing now, what we're going to see is just the kind of final wrap up on this. So we started with finding the work from friction. That was going to oppose our motion. We then found how much work it did by just pulling on this thing horizontally. All right. Once we knew those two works, we were able to find our network. Once we found our network, that was also our change in kinetic energy. After having our change in kinetic energy, we were able to find our final velocity by plugging in our mass and our initial velocity, and then just algebraically manipulating stuff. All right. I will put out some practice problems for you today to look at this and see this so that you can hopefully feel a little bit more comfortable with this stuff. All right. If you have questions, send me an email. Otherwise, we'll see you later. Okay.